time we talked about one of the most profound predictions that comes out of electricity and magnetism, that once you have the coupling between electric and magnetic fields such that changing magnetic fields generate curling electric fields and changing magnetic fields generate curling electric fields and vice versa, then one has the possibility that the electric and magnetic fields self-generate each other. And that leads to the conclusion that electric and magnetic fields generate each other and propagate in free space as waves. A pretty amazing prediction. Comes out of a shocking process. So this was the great triumph of Maxwell's equations. And so what we're going to be doing for the next few lectures is studying the properties of the solutions to these equations. Of course, initially those waves are generated from radiation from the charges and currents. And so we're going to return to put back the sources to understand how these waves arise from time-varying currents and charge densities. But for the moment, we're just going to look at the solutions in free space. Okay? So a particular class that we're interested in are the monochromatic solutions, the solutions that oscillate at a given frequency, omega. And the most general solutions are specified if I just, for example, imagine one component of the field, let's say along the x direction, the most general solution that oscillates at frequency omega is specified by two parameters. Either we can think about it as a certain amount of sine oscillation, a certain amount of cosine oscillation, or equivalently, we can think about that as having a certain amplitude phase shifted from some initial point. So there are two parameters, and we conveniently encode those two parameters as a complex number. Either a real and imaginary part, which we think of as the cosine and sine components, or equivalently an overall amplitude phase. Of course, we have the additional complication that our fields are vectors, so there's those parameters for each component. The x and y and z are each complex components. And that's the waves, unlike the Schrodinger wave function, which is a complex, at least it's the way we formulate it. Whether we can do it in terms of real waves is a whole other story. But here, these are real waves, real fields, because of course the forces are real numbers, and we relate the forces to the real fields. The complex notation is for convenience. Okay? If we have such monochromatic fields, then the wave equation takes a simpler form, whereby we replaced every time derivative by a multiplication by minus I omega. In which case, the wave equation takes a form of what's known as Helmholtz. The Helmholtz equation, which is an equation in three-dimensional space generally, del squared plus some positive number on the wave is zero. That's known as Helmholtz equation. Now, these are really not six independent equations because, firstly, the electric and magnetic fields are not independent of one another. Maxwell's equations, in particular the curl equations, couple them. So, for example, if I'm given the electric field associated with the wave for this monochromatic field, I automatically know at any local point in space what the magnetic field is. Instantly, I know that because the B is related to the curl of E. Okay? So we've gotten rid of 3 equations. We also get rid of another equation because the 3 components of E and B are not independent of one another. The 3 components of E must, for example, satisfy the in free space, the divergence is 0. So there are really only 2 independent degrees of freedom. Okay? Now, we were looking at a particular set of solutions now in terms of the spatial dependence of the fields, and we were looking at the so-called plane wave solutions, in which case the spatial dependence of this complex amplitude varies as a function of position e to the I k dot x with some amplitude for the electric field and for the magnetic field. Okay? And we reminded ourselves of the very basic properties, where if you plug the solution into the Helmholtz equation, you get the dispersion relation, which relates the wave number to the frequency. So K is known as the wave number. The vector K is known as the wave vector. And the relationships that we remember that are easily seen is that the wave number is related to the wavelength of the periodic function. So this is periodic in space with period lambda, which is the wavelength. At a fixed space, as a function of time, the fields oscillate with period t. And the waves are waves of planes of constant field, hence the name plane wave. And those planes propagate at the speed of light. In the phase velocity, generally omega over k, and in free space, omega over k is c. Okay, so that's the velocity at which a surface of constant phase propagates, and it propagates in the direction of the wave vector. All elementary properties we know and truly love. The other things we remember are that the direction of E and B are perpendicular to one another. So the direction of B, or the B amplitude is related to the E amplitude, and the E amplitude to the B amplitude. So they're equal in magnitude in these units, not true in SI units, but true in CGS units. And they're perpendicular to the direction of K. So a linearly polarized plane wave is given here. This is a general linear polarization in some direction, E being a real vector, propagating in the K direction. And the direction of B is perpendicular to the direction of E and perpendicular to the direction of K. And the E and the B are in phase with one another in a free space plane wave. That's not true in a free space standing wave, which you will remind yourself about in the next homework assignment. E and B are not in phase, they're 90 degrees out of phase. Maybe you'll learn that for the first time. Maybe you'll remind yourself of it. Depends. Okay, so the thing we were discussing at the end of lecture was the most general plane wave solution. involves the possibility, if I look in the plane, in this direction, there are two possible orthogonal linear vectors, which I'm calling horizontal now and vertical because I'm fickle about the notation I want to use. Okay? So I have horizontal and vertical linear polarizations in the plane. And the most general electric field that I could write that satisfies Maxwell's equations in free space, that is at a plane constant phase, is written here. So I can have some amount of horizontal and some amount of vertical propagating with the same wave vector and some arbitrary phase associated with those oscillations. Yes?
Shouldn't there be a magnitude of the...
There should, thanks Mark, yeah. There should be p sub v here. It's the amplitude of the v wave, yeah. So we can combine that using the complex notation in terms of a amplitude E naught, which is given by the magnitude of the vector, thought of at some h component and some v component. So the total magnitude is the square root of the squares of those. With some complex polarization vector. Okay, so we characterize the general polarization of a plane wave by a complex vector, not necessarily a real vector, with alpha and beta being complex numbers here. Written here in terms of having some amplitude and some phase. Notice that the way I've written this, the magnitude of alpha and the magnitude of beta are less than or equal to 1. And in fact, the sums of the squares of the magnitudes alpha squared plus beta squared sums to 1 and is given by this polarization vector, which I'm calling epsilon, epsilon star dot epsilon. So this is like the norm squared of epsilon in the complex vector space. When you have a vector space with complex scalars, then in order to look at the inner product, you need to, the dual has a star. And we're familiar with that in psi star psi. Okay? So, we were talking about, and I want to continue that discussion now, about the polarization vector in this complex space and what the meaning is of this. As the other thing we described that I'll just remind you of course, if I look at this thing as the magnitude of this, either h, EH, plus magnitude I, that the overall phase of this thing, so I can factor out whatever overall phase I like. Let's say I factor out that component. That doesn't, this object is the same type of polarization. In other words, how I characterize the polarization doesn't depend on the overall phase of this complex vector. In the same way that you kind of, in quantum mechanics, the overall phase of the wave function doesn't matter. It's kind of like that. And the way we saw that here is that as the wave propagates, or as it evolves in time at a fixed position, you pick up an overall phase, and that changes the overall real amplitude of the field, but it doesn't change the type of polarization you have. Okay? So, for example, as we discussed, if this phase difference is 0, or pi, or 2 pi, or 3 pi, in other words, if it's a multiple of pi, then the polarization vector has the form like this. And what we should see here is that this is real. And it's just in the plane, I have some amount of horizontal and some amount of vertical. And the polarization vector makes some angle with respect to this, depending on if plus or minus the arctangent of the amplitude of alpha over beta, right? No. Yeah, sorry, and look at this backwards. Thank you. Right? So this says that as a function of time, if I were to look at the electric field, it would go back and forth along a line, oscillating with the amplitude, oscillating as a function of time, cosine omega t plus some overall phase as a function of a fixed position. And then it would have E0. And the vector would go back and forth, and this is what we call linear polarization. Okay, so if the polarization vector is a real vector up to an overall phase, it's linear. And the direction of that linear polarization, well, depends on its decomposition into these vectors. On the other hand, if delta phi is equal to, say, I, or pi over 2, excuse me, then the polarization vector is equal to alpha EH plus I beta EY. Sorry. So in this case, let's consider this case for the specific case that alpha equals beta. Okay, and since this is normalized, then that has to equal 1 over root 2. So then this is equal to EH plus I EV over root 2. Okay, so if I look at this specific case, and I look at what the electric field is as a function of position of time, what is it? Well, we plug in, this is the real part of E0 EH plus I EV over root 2 e to the I k dot x minus omega t, where I've set the overall phase to be 0, just for a point of reference. So what is this when I take the real part? Well, I got an E0 over root 2. Then I take the real part of this, which is cosine. So EH is a real vector, cosine k dot x minus omega t, plus E0 over root 2 ED sine, or minus sine. Everyone agree that this is minus sine? Because the real part of I times e to the I something is, well, if I multiply this is cosine of the thing plus I sine of the thing. Multiplied by I, that's minus 1. Take the real part, I get minus 1. Okay? So, let's look at this for example. It doesn't matter. Let's consider what is the electric field at the position, the origin, as a function of time. That's equal to E0 over root 2 cos omega t in the h direction plus E0 sine omega t in the v direction. Because sine of minus omega t is minus sine of sine of minus, yeah, anyway, that's right. Okay? So, what is this vector doing in the plane, horizontal, vertical, as a function of time? It's rotating, right? It's rotating at time t equals 0, it's over here, E0 over root 2. At when omega t, this is when omega t equals 0. What happens when omega t is equal to pi over 4? That is an eighth of a period later. Well, then it's sitting over here, making that angle. When omega t is equal to pi over 2, cosine is 0, sine is 1, and thus it goes around in a circle. And you can think of the very creative name that is given to this polarization state. It's called circular polarization. Often E plus. Okay? So circular polarization, remember here, the wave vector is coming out of the board. Here is the way I've drawn it. And the wave vector goes around, sometimes known as right-hand circular polarization. Now there's a little bit of a confusion about this that I'm actually not exactly sure about. Here, I've called this right hand, but I'm looking at the wave coming at me. I think in optics, there's some inconsistency on how this is discussed, and sometimes right hand is looking at the wave going away from you. Okay? That's a confusing thing. It's a better thing to call this, for reasons that we'll explain better, positive helicity. That is, has no ambiguity associated with it, which is to say, if you put your thumb along the wave vector, if it's the right-hand rule, then it's positive helicity. Yeah?
So presumably negative would be the other way around.
The other way around. So if this is equal to minus pi over 2, then this is minus, and this would be minus, this would be minus, this would be plus, and this would be minus, and then it would go the other way. Okay? So if we have our polarization vector where the magnitude of the two components are equal, but their phase difference is plus or minus 90 degrees, then the effect of that is circular polarization, which means if I'm sitting here, what I'll see is the vector going around in a circle. Of course, what that means, at a fixed time, as a function of space, the vector looks like a helix. So that when that helix is coming to me, it goes around in a circle, right? But at a fixed time, as a function of space, it looks like a helix. Is that clear? What would happen if we have delta phi is equal to plus or minus pi over 2 modulo 2 pi, but alpha not equal to beta?
spiral?
You would still have a spiral, but what would it look like at a fixed position as a function of time? What would the curve be that it traces out? And it'd be an ellipse, right? Because in that case, if alpha doesn't equal beta, what I would have is that, say, at the origin again, as a function of time, now I would have the same kind of function but with the horizontal and vertical amplitudes not equal. So this curve would be an ellipse, which is with its major and minor axes along the h and v axes, depending upon which is bigger. In this case, I've made EV bigger than EH. And it would go either this way for the phase being pi over 2, and it would go the other way if the phase difference was minus pi over 2. So what do we call this? Elliptical polarization. Boy, we're clever. Okay. Now, more generally, if we have a general alpha and beta, we have generally some ellipse at some funky angle with some ellipticity. Now, this is not trivial to show, and I'm going to skip the details. It involves some, analytic geometry and all your conic sections or whatever your favorite ellipse geometry that you've forgotten is. But the point is that when general alpha and beta, we have a general ellipse. Are there two L's in ellipse?
Yeah.
Yeah. Maybe it didn't look right. And the degree of ellipticity depends on the magnitude of alpha over the magnitude of beta. If this is 1, then it's pure circular. If it's 0 or infinity, then it's linear, and anything in between is an ellipse of a finite ellipticity. All right, now, one way in which we can specify the state of the polarization that tells us immediately what kind of polarization we're talking about, the amount of ellipticity, is to think carefully about this complex vector and how we can easily parameterize it. And so I'm going to introduce the notion of the Poincare sphere and the Stokes vector. Classical optics notions. Okay, so let's look again at our polarization vector. In particular, I'm going to look at the polarization vector as having a certain amount. I can always write it in any basis I like, and the E plus and the E minus vectors form a basis for this complex plane in the same way that EH and EV did. Let me, for simplicity, let me call the H direction the X direction and the V direction the Y direction. That's a particular choice. In which case, E plus and minus are EX plus or minus I EY over 2. Now, I should mention, in the context of as you know, there is an intimate relationship here between the spherical basis and angular momentum and the theory of spherical harmonics. And sometimes you will see an overall phase out front here, minus plus, which has to do with the theory of angular momentum. In this case, it's not so important, and so I'm not going to carry around that extra. As we said, the overall phase doesn't matter in terms of how we define the polarization vectors. But I just want to mention it to you because it gets confusing sometimes when you're working on irreducible spherical tensors and so forth. You've got to keep around that extra minus sign. Put that aside for the moment. Okay, so everyone buy that I can write an arbitrary vector this way, where if it's now, we said the question is how many real numbers do I need to specify this vector? I have two complex numbers. It looks like I need 4. But that's not true because the overall phase doesn't matter in terms of characterizing the vector. So I'm just going to factor that out and assume that I keep this guy real and put an overall phase, I'll call it phi. So that's equivalent. This equivalent type. Let me, instead of, just call it alpha and beta, I don't know why I put stupid labels on it. Let's call it alpha and beta. Minus. Okay. So now I have 3 numbers. The magnitude alpha, the magnitude of beta, and this one phase. But of course, if it's normalized, that's, these guys are not independent. In fact, the magnitude of alpha squared plus the magnitude of beta squared is equal to 1. So the magnitude of beta squared is equal to 1 minus the magnitude of alpha squared. So there are only 2 numbers that I need, just 2 real numbers to specify the polarization state. And in fact, the fact that the magnitude of alpha and the magnitude of beta, when squared, add to 1s means that there's a natural parameterization. You know, cosine squared plus sine squared is 1. So I can specify alpha and beta by an angle. And by convention, we define the magnitude of alpha as cosine of some angle theta over 2. For reasons that will become clearer in a moment. And magnitude of beta then is thus sine of theta over 2. In which case, the polarization vector is in one-to-one correspondence with these 2 angles, theta and phi, written here for some reason as phi and theta. Where phi goes between 0 and pi, I mean 2 pi. I'll just leave the endpoint out. That gives us different polarization vectors. And we can see here, because of the way the magnitude works, that's why we have this theta over 2. This only goes between 0 and pi. Because when theta goes to pi, cosine of pi over 2 goes back to 1. Goes back to itself. So, we see here there is an isomorphism, fancy word, there is a one-to-one mapping between the unit vectors in a 2-dimensional complex vector space and a sphere. They are in one-to-one correspondence. Every point on the sphere can be thought of as specifying a unit complex vector up to an overall phase. Now, we may We know about something like that when we think about quantum mechanics and a spin 1/2 particle. All spin 1/2 particles represented by spin up along some direction. That we call the Bloch sphere. This is the same thing, it just has another name, which was invented in optics years before by none other than Poincare, called the Poincare sphere. And there is one-to-one correspondence. So let's think about now how all the different polarization states of a plane wave can be specified by a point on a sphere. Let's think about that for a second. So, first of all, let's look at the case, consider the equator. That's the place where theta is equal to pi over 2. Okay? So, when theta is equal to pi over 2, then the magnitude of alpha is equal to the magnitude of beta is equal to 1 over root 2. Right? Because cosine of pi over 4 and sine of pi over 4 are both equal to 1 over root 2. So in that case, my polarization vector is equal to E plus e to the I phi e minus over root 2. Right? These are the points on the equator. What kind of polarization is that? It's not so obvious here because this is already in the circular language. I should have done the poles first. Why didn't I do that? Let's go backwards. Pole. North Pole. Theta equals 0. Beta equals 0. Alpha equals 1. So what kind of polarization is that?
Circular.
That's pure E plus,
Circular.
which is pure circular, right hand or positive helicity. What about the South Pole?
Negative.
That's pure E minus, right? In that case, the South Pole is beta, this is equal to theta is pi, sine of pi over 2 is 1, cosine of pi over 2 is 0, so that's some overall phase that doesn't matter, E minus. Now let's go to the equator. In the equator, this is true. So that's not obvious what it is, but one way to look at it is the following. Let's plug in Ex and Ey for E plus and E minus. Okay? So we got Ex times 1 plus e to the I phi over 2. And then E minus is equal to that, so I get plus I dy 1 minus okay, we buy that. Plugging in for E plus and E minus. And now I gotta have my alpha and beta, huh? No, that I already did that. Alpha and beta are 1 over root 2, so that gives me that root 2. I think I did that right. I don't remember the signs is bothering me. I'm going Okay, so let's write it down then. So now what the heck is this? Well, it's not so obvious, but if I factor out an overall e to the phi over 2, then this is equal to ex e to the I phi over 2 minus e to the minus I phi over 2 over 2.
Plus, right?
Yep.
You need a plus sign.
It's not plus, thank you. That one's right. And then I have plus I e to the minus pi over 2 minus e to the I pi over 2 uy. What's this?
Cosine.
Cosine. And what's this?
Minus sign.
Sine with an I in there. Which is what the means. But it should have been minus I and then check that at some point. Equal minus I. Oh, that's right. Okay, good, it worked. Yeah. Okay, so the bottom line is on the equator, the polarization state is some overall phase times cosine phi over 2 ex plus sine phi over 2 ey. What kind of polarization is that?
Linear.
Linear. The overall phase is irrelevant. This is a real vector in the xy plane. Therefore, this is linear polarization. And the direction of the polarization is the following. So here's the Poincare sphere. Here's phi equals 0, here's theta equals 0. At the top, I have right-hand circular polarization. At the south pole, I have the opposite. Here's phi equals 0. When phi equals 0, I have x polarization. When phi equals pi over 2, what do I got? 45 degrees, right? Because when phi is pi over 2, I get 1 over root 2 ex. So at phi equals 0, theta equals pi over 2. Let's just write it out. My polarization is x when theta is equal to pi over 2 and phi is equal to pi over 2, epsilon equals ex plus ey over root 2. So this is at 45 degrees. What about when theta is pi over 2 and phi is pi? Pure y. And when I go around the sphere some more, I'm at negative 45 degrees over the other 45 degrees. So this is at 45 degrees, and this is at minus 45 degrees. So as I go around the equator, the polarization goes from horizontal to 45 degrees, to vertical, to minus 45 degrees, back to horizontal. Notice, points on opposite sides of the sphere are orthogonal. Just like in the block sphere, you got spin up and spin down. The angle between the polarization is equal to half of this angle on the Poincare sphere. That's what I got. Now what about the points not at the poles, not at the equator, but in between. Clearly, they are elliptical. And it goes kind of like this. This becomes an ellipse like that, and this becomes an ellipse going the other direction. We got an, or if I go at 45 degrees, I got an ellipse that is at 45 degrees. Now this goes the other direction, etc. So you will see in optics a way of characterizing all polarization states as points on this sphere. That sphere is called the Poincare sphere. And we can specify it by just these two angles, theta and phi. Okay? Now, there's one last ingredient that I want to discuss, which is if I wanted to call the point on the sphere by, there's some point represented by a vector, which has components along these three axes that I call 1, 2, and 3. So I can specify the polarization vector now by this vector, okay, which is specified on the sphere by theta and phi, but I can also specify it by three components: a component along the 1 axis, a component along the 2 axis, and a component along the 3 axis. That vector on the Poincare sphere is known as the Stokes vector, which is discussed in Jackson, although he doesn't discuss the Poincare sphere quite in this detail. The Stokes vector is a classical concept. Stokes, I don't know when he was around, probably sometime in the 19th century. I'll leave it as an exercise. So how is the Stokes vector defined? It has three components. S1, S2, and S3. Stokes vector S. Not to be confused with the Poynting vector. The S1 component is equal to the amount in X compared to the amount of Y. The 3 component is equal to the amount in right-hand circularly polarized minus left-hand, or positive helicity minus left. And the S2 component is the amount in 45 degrees minus the amount in minus 45 degrees. Where I've written the vector in 3 bases. That's to say, epsilon is equal to an alpha plus E plus an alpha minus E minus, or equivalently, it's a certain amount of X and a certain amount of Y, or equivalently, it's a certain amount of 45 degrees and a certain amount of minus 45 degrees. Any one of these forms a basis for the space. So if I tell you the relative amount of X and Y, and the relative amount of 45 minus 45, and the relative amount of circularity, then I specify the polarization. Yes?
We took optics,
Mm-hmm.
and actually Stokes vector has the unpolarized component.
That's correct. So this is so let me make I was going to make a statement about this. This is for pure polarization. Every state, I mean, if we want to talk about, so right now I'm talking about the much more simple case of pure coherent light. If I have pure polarization, I put something through a polarizer of some kind, then it's a point on the Poincare surface of the Poincare sphere, in which case the Stokes vector has magnitude 1. Okay. However, the light that's coming out of this beautiful fluorescent light bulb that's bathing you with the most pleasant light that you can possibly be in is not perfectly polarized. In fact, it's made up of jiggling electrons, which make my eyes hurt, in some random way colliding with the neon inside those tubes, such that the X component and the Y component aren't necessarily coherent with respect to one another. So I don't have a coherent superposition of these, but I have some random jiggling of those, in which case we talk about statistical mixtures rather than coherent superpositions. That's a concept from classical optics as well as quantum mechanics, in which case the Stokes vector can represent the state of unpolarized light as a vector which has a statistical mixture of these components, and they're represented by Stokes vectors inside the Poincare ball. In fact, the center of the Poincare ball is completely unpolarized light. And you may, for those of you who are the aficionados in quantum mechanics, recognize this as the states of the density matrix for a spin 1/2 particle. The surface of the sphere are the pure states, and the states inside the sphere are the mixed states. It's the same math. All right, cool. All right, so that's plane waves as far as characterizing them. Now, one of the things that we talked about just recently, of course, is that the waves carry energy and momentum. Oh, I'm sorry, electromagnetic fields can carry energy, momentum, angular momentum. So let's talk about that in terms of what the energy and momentum is in the waves. So recall the energy density U is equal to 1/8 pi, the magnitude of the electric field. In this case, it can generally vary as a function of position and momentum, and the same thing for the magnetic field. And the Poynting vector, which represents the energy flux density, as a different S, not that S, totally different, is C/4 pi E cross U. So, let's look at this for the case of monochromatic fields of this form. Regardless of whether they're plane waves or not, let's just look at them for monochromatic fields. Now, quite often it's the case when we're talking about electromagnetic waves, is particularly if we're talking in the optical domain, where the frequency, say, is, hundreds of terahertz, 10 to the 15 hertz, or something like that, that we're not interested when we're talking about the force on detectors, for example, in terms of the instantaneous force, but something, what is the force on average, because it's oscillating so fast. So quite often we're interested in the, for monochromatic fields, we are often interested only in time averaged energy. averaged over a period. And there's a very convenient formula that we can use when our fields are monochromatic to write down the time average. So let me do a famous aside over here. Suppose I have two functions that are just functions of time that are oscillating with frequency omega. So there's some complex amplitude of this function, right? It's got some A cos omega t plus B sine omega t. Right? So F is A plus IB F tilde. And let's say I have some other function which has some complex amplitude e to the minus I omega t. Let's say C cos omega t plus B sine omega t. So G tilde is C plus IB. Okay? So now I ask you, what is the time average of the product of f and g as real functions? Well, if I plug this in, when I multiply it, I'm going to get a times c cosine squared and b times d sine squared. We know that the time average of cosine squared and sine squared are 1/2. But we're also going to get the cross terms, cosine times sine, which is sine of 2 omega, which average over a period is 0. So when you do all this out, you will quickly find this is AC plus BD, which is equal to 1/2, oh, I'm sorry, over 2 at the cosine square and sine square. 1/2, the real part of F0 tilde star G0. Or equivalently, that. So, this is a very convenient formula. If you have monochromatic functions and you want to find their time average, you can do it simply by just looking at the complex amplitudes and multiplying them in the conjugate form and then taking the real part in the end, the factor 1/2. Of course, if I have vector functions, then I have to do that for each component, so I have to also take the dot product when necessary. So, given that lovely factoid, we can quickly see the following. The time average energy density in the field is equal to what? Well, it's equal to 1/2 the real part of E tilde for the first thing, and then I got it over 8 pi. And then I got to erase a lot more. plus 1/2 the real part of b tilde star x b tilde over 8 pi. And of course, this is the magnitude of the complex vector, both in magnitude in complex sense and magnitude in vector sense. As such. Okay? So that's the time average energy density in the field. Now, let's look at this for the case of the plane wave. For the plane wave, the complex vector Ex is E0 e to the I k beta x, and B is B0 k beta x. And so this is equal to 1 over 16 pi B0 squared plus B0 squared. Right? The phase connected it, you take the complex absolute value. And what about E0 and B0 for a plane wave?
Same thing.
Their magnitude is equal. So in a plane wave, which is what we're talking about, the magnitude of E0 is equal to the magnitude of B0. What that means is that the energy in the electric field for a plane wave time average is equal to the energy in the magnetic field. And the total energy density then, time averaged, is then equal to 1 over 8 pi, the magnitude of the electric field vector squared. Okay? Sometimes known as epsilon over 2. Epsilon not over 2. All right, what about the Poynting vector? So the Poynting vector, again, we can look at the time average of the Poynting vector as a function of position. This is known as the intensity of the wave. Right? This, what are the units of the Poynting vector? It's the energy per unit time, per unit area, or the power per unit area. That's the intensity. And for a plane wave, what is that? Well, the intensity, I, is equal to the real part of E star, generally for monochromatic field, it would have this form. 1/2 of that times C over 4 pi. And for a plane wave, this is equal to C over 8 pi, E0, the real part, of E0 star crossed into B0. What is this equal to? Well, the direction of E cross B is the k-hat direction, right? And so for a plane wave, this is then equal to, since these guys are equal in magnitude and they're perpendicular to one another, the cross product is the magnitude of E tilde, the magnitude of B tilde, times k-hat. And the magnitudes are equal, so this is equal to C times E0 squared over 8 pi in the k-hat direction. But we just said that E squared over 8 pi was the total energy density in the wave. So the Poynting vector, intuitively then, when time averaged is equal to C times the time averaged energy density in the k-hat direction. Does that make sense? Maybe. It's maybe too late in the lecture to make too much sense of it.
Power of the direction of the propagation.
Yeah. So let's remind ourselves, recall, for flowing current or for flowing charge, we said that the current density was equal to the charge density times the local flow of this. What this is saying is exactly this. Instead of charge density, we have energy density. It's flowing at the speed of light. The flow of energy density at that speed is the flux density of energy. Just like we had the flux density of charge was the current density. This is for plane waves in free space. Okay, so a few things that we just learned is that in a plane wave, the amount of energy density time average in the electric field is equal to the amount in the magnetic field. The energy density time average in a plane wave is uniform in space, obviously not physical because its energy fills all space. And so if I were to average, or not average, but integrate over all space to find the total energy, I would get infinity. So don't exist. Nonetheless, as we discussed, we talk about plane waves because of their nice mathematical properties, because they are approximations to real waves, and because they form a nice Fourier basis, which is our next topic. And given the lateness in the day, I was going to say it's spring break. We'll call it quits and figure out what we're doing.